The objective today is to explain why encryption is an important need for everyday life on the internet. So before we dive deep into what public key cryptography is, I want to do a little review by using some comics. So starting with this one, password entropy is rarely relevant. The real modern danger is password reuse. This guy says, how so? Set up a web service to do something simple like image hosting or tweet syndication. So a few million people set up free accounts. Bam, you've got a few million emails, default usernames, and passwords, which is a very scary thought, and which is a reason you should use apps like KeyPass, or there's more than one out there. So as long as you're using a different username and password for every site, or at the very least, using a different password for every site, you should be good to go. The next comic is kind of funny. The only thing I like more than weak crypto is my enemies using it. Extra credit opportunity right here to tell me what WEP means. Another Dilbert comic. Here's a tour of accounting. Over here, this guy says we have a random number generator. 99999. Are you sure that's random? That's the problem with randomness. You can never be sure. And the last comic, a crypto nerd's imagination. So when you really get into hacking, you might be like this. You might think, this guy's laptop's encrypted. Let's build $1 million cluster to crack it. Obviously, that would be impossible if the guy's using 4096-bit RSA. And we're going to learn about RSA a tad bit today. So then, blast, our evil plan is foiled. This is a little bit more closer to what would actually happen, reality. It says his laptop's encrypted. Drug him and hit him with this $5 wrench until he tells us the password. Got it. So we've learned a lot about what cryptography means and what encryption is using ciphers. Your real task right here is not to give me a multiple choice answer, but to do this think, write, share, using the multiple choice question to help you reflect. The question is, what problems exist with encryption schemes such as a Vigenère cipher, even when strong encryption keys are used? So the multiple choice question says, why are computers better than humans at breaking encryptions, such as the Vigenère cipher? Well, the first one says computers are smarter than humans. That doesn't make much sense. In some cases, they are more useful. In other cases, humans are more useful. B says computers are faster than humans. That's true like 90% of the time, depending on the task. C says the Vigenère was originally designed by a computer. That makes absolutely no sense. The Vigenère was obviously being used before computers were around. But this answer makes me think some artificial intelligence is the reason why we had it. But okay, that's just not an accurate answer. And then D says they are not. Humans are better at breaking Vigenère encryptions than computers, and that is definitely not true. Computers can do a lot more checking and guessing than we can. And so that must mean B is the correct answer. Computers can guess and check faster than humans can. So even when the Vigenère cipher is using strong keys, it can still brute force that password to try to figure out what it is. Or brute force the message itself, the ciphertext itself. Now in this one, go ahead and put 2 letters. Why is a Vigenère cipher hard to crack? One cannot solve using frequency analysis directly, so that's correct. The second one says long keys create exponential growth possibilities. That is also very correct. If you remember in my past lessons, I talked about using a pattern and nonsensical things to create a password, and the longer the better. C says the key is always secret to both the sender and receiver of the message, and that is definitely not true. In a Vigenère cipher, both parties need to know what the key is, and there is only one key in this scenario. D says a Vigenère cipher relies upon an alphabet shift algorithm. So though this is true, there is some sort of shift going on. The shift is being based on the key and is not used with fidelity throughout the entire ciphertext. That exact same shift. So therefore D cannot be correct as either. That leaves A and B. So complete the following sort. Choose 3 words that are tricky or tough to write out in the think, write, share. So I really do like this link and this exercise. Here we are looking at the matching that I'd like you to do, and so basically through trial and error figure out where these definitions go. And then at the end, I want you to choose 3 to tell me what they mean. And then in the end, I'd like you to choose 3 that are tricky or tough so you can write them out on Canvas. And that way I can do some reflecting as a teacher as well to know what you guys are having a hard time with. So let's go through these quickly together. That way there's no excuses for you not to know what the correct answers are. So computationally hard is a problem that cannot be solved in a reasonable amount of time. The Vigenère cipher, how should we do this? Encryption in which arbitrary symbols replace letters. Okay, I think that's actually in the right spot with random substitution. This says use an algorithm to decode a message. So decrypt. When you decrypt, you use an algorithm to decode. And then here's the opposite, using an algorithm to encode. Encryption that shifts the alphabet differently per character. Oh, that's definitely the Vigenère. Another term for encrypted message. Okay, that's what a cipher is. And the last one, the Caesar cipher, must be an encryption scheme based on shifting the alphabet. So of all those words, just choose 3. If you want to learn more about cracking codes and passwords, I have several links for you here, starting with an article from Wired magazine called Cracking a Code as the Key to Understanding Ancient Culture. Someone else created a video on cracking the human genome. That's a fascinating one. The third one is Nobel Prize given for cracking the code of DNA, so you could go to nobelprize.org to learn about cracking the code of DNA. Then you have the Navajo Code Talkers, which is a fascinating code to study. And then last but not least, this is probably my favorite, the Vigenère Cipher Cracker Tool on Simon Singh's website. This is a famous author. And right here is the website I was talking about. So basically it's called the Black Chamber, and you can have a bunch of ciphertext right here, and there's an analysis that goes on. Is basically for the sake of figuring out the possible length of the key in the Vigenère cipher, and you can tell just by looking at this that the possible length is probably 7 letters long. And so when you go down here, they'll give you some instructions and you can read through this on your own. We definitely do not need to go that deep into how ciphertexts work. Okay, so diving into the meat of today's lesson, this is a big multi-part lesson that introduces the concept of public key cryptography. I did you guys a favor and took most of the math stuff out and put it in the next lesson. So today, if you walk away with the knowledge of what public key cryptography is and why that is just such an important thing to everyday life, then I'll be happy. So now, public key cryptography, which is an answer to the crucial question, how can 2 people send encrypted messages back and forth over insecure channels, that is the internet, without meeting ahead of time to agree on a secret key? In a nutshell, there are 2 main principles. The mechanics of communication with public key cryptography. That part of the lesson is going to be pushed back to the next video. And then this one, the basic mathematical principles that make it possible. We'll talk about those principles, but you don't have to really do any action today, okay? So this is a fairly hefty lesson because the underlying ideas are subtly quite sophisticated. It's worth noting that much of the material here are all but the highest level takeaways. I'll try to differentiate what's beyond the scope of what's covered on the exam while going through these lessons. What you will need to know is the basic process of public key encryption and what asymmetric encryption is. Now for programming, you'll need to know how the modulo operation works, so this is used not only in cryptography but also in programming. Now don't forget, programmers create the algorithms and create the operations that ensure your messages are encrypted. So think right share here, what 3 things do you need to know? Our purpose here is to reveal some of the magic that happens every day on the internet to enable secure transactions. To many, the fact that encrypted messages can be sent between 2 parties who have never met before is taken for granted and opaque. Our belief is that understanding how it works with some depth, getting to experiment with the mathematical principles that make asymmetric keys possible, and the resulting encryption hard to crack, is deeply satisfying. So all that just to say, this is a really fun topic to cover. The widget we'll use in the next lesson mimics the RSA encryption algorithm with small numbers and slightly easier mathematics. So what I'm doing here is using real encryption methods used by real experts to teach you how the cryptography works. And I'm not linking you to the widget quite yet, not only because that's for the next lesson, but I really do want to encourage you to check out some of these other links. Public key cryptography allows two people who have never met and who haven't agreed on a shared key to send encrypted messages that only they can read, using insecure channels. Arithmetic can be used to encrypt a message which only an intended recipient can decrypt and read. Using a public key and private key, messages can be encrypted and transmitted securely, even if the message itself and the method used to encrypt it are both public. The modulo operation, or clock arithmetic as we call it in the lesson, is a real one-way function that is used for asymmetric encryption. The modulo operation gives a remainder of a number. So your think, write, share here is what makes asymmetric encryption work. Now let's talk a little bit about the vocabulary we've used so far today. Modulo is the name of a mathematical operation, and here is just another example in case you need it. 17 mod 13 is 4. So when you divide 17 by 13, 13 can only go in once, and what is remaining is 14, 15, 16, 17, so 4. Asymmetric encryption is a type of cryptography based on algorithms that require two keys, one of which is secret, aka private, and one of which is public. That means it does not matter if the public knows that key. Public key is a value that can be used to encrypt a message, and then the private key is the complementary key to the public one, right? That is used to decrypt. So that's a good way if you're jotting down notes to differentiate between public keys and private keys. So your think, write, share, which vocab word do you think would be the most challenging to remember here? Realize the difficulty of the problem. No form of symmetric encryption will work. There's no way for parties to establish a shared key without agreeing ahead of time in a way that secures it from an observer. So symmetric encryption is a real pain and very, very hard to do, or very hard to keep secure. If you want to watch a video to understand public key cryptography, I highly suggest this one. If you're in my class, I'll post it in Canvas. If you're on YouTube, I'll provide the link in the show notes. So that's pretty much it for today. I just want to do a quick preview for next time, just something for you to think about because we're going to use this modulo operation quite a bit. It is still just math. For example, in classic division, 13 divided by 5 is 2, remainder 3. Now, using this operation, all we're looking for is the number 3. You can look at the graphic a little bit more to understand what I'm talking about. There's a well-known visual analogy for modular arithmetic using clocks, and since modulo is often thought to wrap the number system, if, for example, you use 12 as a modulus, then any result must be in the range of 0 to 11. Since those are the only possible remainders. Similarly, no matter how many hours you count off on a traditional analog clock, there is a limited number of hours, 1 through 12, that the hour hand can be pointing to. It's even called clock arithmetic in some places. If you want to know more, I would suggest going to Wikipedia and searching for modular arithmetic. And I really like this phrase here. Using modulo operations, the output obscures the input. So it's time for our IB questions, and since we're getting deeper into programming, I want you to think of this in the context of programmers. What will they look like when a programmer is open-minded, is caring, is thinking, etc.? So here's your list of fill in the blanks for the sentence. Go ahead and choose one. And here's the DOL. Why is it important to use public key cryptography such as the Diffie-Hellman key exchange? Don't get bogged down by the vocabulary. Just tell me why it is important to use public key cryptography.